Okay, let's take a look at another example of an iterated integral over a general domain. After seeing the last video, let's see if you can do this one yourself. So I'm going to ask you to pause the video as we go through the steps of this. So the problem is to set up and evaluate the double integral of the function f of xy equals 3x squared y over the region bounded by the curves y equals 5 minus x squared and y equals 3x squared minus 2x minus 1. So the first step is to graph the region. So go ahead and either graph this by hand. Actually, you should be able to sketch a quick graph of this by hand, or you can also use some technology to help you with this. So pause and then come back when you have the graph. Okay. Now you should have gotten something that looks like this. Now the next thing we want to find is we need to find these intersection points on the curve and find out what these boundary points are here and here. It looks like one of those might have really nice integer coordinates, maybe not for the other one. So we're really solving this system of equations, y equals 5 minus x squared and y equals 3x squared minus 2x minus 1. So solve this and then come back when you get that done. Press pause now. Okay, solving this system of equations can be done by substitution. So you can take the 5 minus x squared, which is y on the first curve, replace the y in the second curve by that, and now we have an equation that has only x's. We're going to add x squared and negative 5 to both sides to get 0 on one side, and so that results in 4x squared minus 2x minus 6 equals 0. We want to factor that if possible, so I'm going to factor out a 2 first, leaving 2x squared minus x minus 3 for the other term, then using anti-FOIL factoring, or we can factor this as 2x minus 3 times x plus 1. Well, 2 of course is not 0, but 2x minus 3 might be 0, or x plus 1 could be 0, or the possible solutions. If x plus 1 equals 0, then x equals negative 1, and if 2x minus 3 equals 0, we add 3 and then divide by 2 to get x's 3 halves. Okay, so this is at negative 1 for x, or at x equals 3 halves. If we have x equals 3 halves, then we plug it into one of these equations to find y. It could be either one. Looks like this one might be the easiest, so I used it. 5 minus 3 halves squared because x is 3 halves. Let's see, 3 halves is 9/4. 5 is 20/4 minus 9/4 is 11/4. So that says this point here, where the two curves meet in the first quadrant, is the point xy equals 3 halves, comma 11/4, or in decimals 1.5, comma 3.75. And if you look, that does seem to agree with the picture that we have. If we have the other point is when x equals negative 1, plug that back into the original equation of 5 minus x squared for y, and that should say negative 1. But of course, negative 1 squared is still 1. 5 minus 1 is 4. So that the point is negative 1/4, which we can definitely see that one on the graph as being correct. Okay, so we have that. So now we have to decide whether to set this up by using a vertical strip or horizontal strip. If we try to use a horizontal strip, up here it's bounded by the red curve, the upside down parabola, here, and here on both sides. Here it's on the right by the red one, on the left by the green one. Down here it's on the right and left by the green one. We would have to break this into 3 regions. We'd have to solve in terms of y, which would be too bad for the first one, but really nasty for the second one. So that's not a good option. It's pretty straightforward, however, if we use a vertical strip. The top curve is always the same, and it's already given in the form y equals some function of x. And the bottom curve is always the same down here. Again, given in the right form for us. So it's easy to get everything in terms of x, and so that means we're integrating with respect to y first. So see if you can set up the integral. When you think you have it, come back. Press pause now. Okay, so of course the function that we're integrating is 3x squared y. That's the given function, so that's the integrand. That's what goes right here. We're integrating with respect to y first. Well, where does y run? If we look at a vertical strip, the bottom of it goes from the green curve, the top is on the red curve. So the green curve, the right side up parabola, the y is given by 3x squared minus 2x minus 1. So that's our limit for our lower limit of our integral. And the top is 5 minus x squared. That's our top limit. And so that's what y is running from. X then, being the outer integral, is going to just go from some constant to some constant. And so the minimum x we see is -1 right there at that point, and the top one there is 3/2. Now you can see why we needed to find those limits of those intersection points there to get the outer limits here. All right, next step is to go ahead and do the iterated integral. Okay, so go ahead and work on that, and then when you get an answer, come back and we'll check it with the work here. Press pause now. All right, so here we go. Here's our integral that we've set up. So first we're integrating with respect to y. That's just a constant times y. So the antiderivative is going to be y squared, and we're going to divide by 2. And when we divide by 2, that 4 becomes now a 2. And the another thing that we could have done actually from the start is that 4x squared is like a constant when we integrate with respect to y. It could be brought out front of that first integral sign. It's essentially the same thing as we've done here. We're just going to evaluate the y squared part. Okay, so now we just plug in 5 minus x squared in place of the y, and then this quadratic here, 3x squared minus 2x minus 1 in place of the y here. We have to square both of those things. So we have to square that out. Okay, that's going to be x squared is x to the 4th. Multiply and double for the middle, and here 5 squared is 25. You can square this one out by doing long multiplication, 3x squared minus 2x minus 1, put 3x squared minus 2x minus 1 on the bottom, multiply the -1 times each, the -2 times each, the 3x squared by each, and then add up like terms. You'll get 9x to the 4th minus 12x cubed minus 2x squared plus 4x plus 1. The minus is from the fundamental theorem of calculus there. Distribute the minus and combine like terms. We've got a minus 9x to the 4th and plus 1x to the 4th is minus 8x to the 4th. We've got minus 12. Well, 2 minuses makes plus 12x cubed. And x squares, we got -10x squares here, and 2 minuses makes plus 2. X squares there makes -8x squared. We've got the x's are here, 4x makes it negative here, -4x. And then 25, and then minus 1 is 24. The 2x squared, notice, was along for the ride here for a while, and now it has to be multiplied across, distributing. Actually, what I'm going to do is I'm going to distribute the x squared, which makes the powers go up to 6, 5, 4, 3, and 2, but I'm actually going to factor out a -4 along with the 2 makes a -8, and I'm going to pull that out front. So ultimately the coefficients inside here are going to be divided by -4. -8 by divided by -4 is +2. 12 divided by -4 is -3. -8 divided by -4 is 2. -4 divided by -4 is 1. And 24 divided by -4 is -6. So just got that out of the way. Started with the leading coefficient is positive and so forth. Okay. Now what do we have next? We take this and we're doing just a calculus 1 integral with respect to x. So the antiderivative is pretty easy, just a polynomial. add 1 to the power, divide by the new power. So that goes to the 7th power, divide by 7 is 2/7. That goes to the 6th power, -3 divided by 6 is -1/2. Goes up to power 5, divided by 5, that's 2/5. That goes up to power 4, gives us 1/4 for the coefficient. This goes up to 3, -6 divided by 3 is -2. Evaluate from -1 to 3/2, and then don't forget to multiply by the -8 at the end. Some little bit of nasty fraction arithmetic here, but take this right here, plug in 3/2, and then minus the same formula, plugging in -1. Let's do the easy part first on the right. So there's 3, 4, 5 negatives there, makes a -2. 4, 5 negatives makes a -1/4. 5, 6 negatives is a positive 2/5. And 6, 7, 8 negatives, that's an even number of negatives, that's a positive 1/2 there. And 7, 8 negatives is a positive 2/7. So the one on the right was not too hard. Now this is just some arithmetic here that you might want to get a calculator out to help you with, but 3/2 to the 7th times 2/7. Well, one of the 2's cancel. So you got 3 to the 7th over 7 times 2 to the 6th. That's 2187 over 448. And in a similar manner, you can see these hopefully on the screen here, what these all turn out to be. Get a common denominator and add those together. I used a calculator to help me with this. And don't forget to multiply by -8 at the end. And you end up with 3,875 over 112. In exact decimal form, that's 34.5982, and then a repeating pattern of 142,857, 6-digit repeating pattern there, repeating over and over at the end. And this does check out with the TI Inspire CAS. So that gives you another example of an iterated integral. So hopefully you can work some homework problems over this, check this against other examples in your textbooks, and get some practice doing these kinds of problems.